Don't say anything you don't want YouTube to hear.
Hello, everyone. Hi. Yes.
We're gonna start.
Yeah, hello everyone. Welcome to the first seminar and the first colloquium of the Severo Ochoa IAA program in 2026. Our speaker today probably does not need any introduction for any of you people here at the IAA, because he's a good old friend of the house. But for people outside, our speaker today is Dr. Carlos Carrasco. Charlie for the friends. He got a PhD, a bachelor's in physics in the Universidad de La Laguna in the Canary Island in 2010. Sorry, the PhD in astrophysics 24. Yeah, the PhD in astrophysics from the University of Granada, working here at the Instituto de Astrofísica de Andalucía in 2010. Now it's the good year. And he has been a researcher at the Universidad Nacional Autónoma de México since 2013. So his research is focused on the study of astrophysical jets and protoplanetary disks, mainly through radiointerferometric observations. So among his works stand out the use of the ALMA and VLA interferometers to study magnetic fields and collimation mechanisms in protostellar jets, as well as the evolution of dust and planet formation in protoplanetary disks. Dr. Carrasco is currently the head of the graduate program in astrophysics at the Instituto de Radioastronomía and Astrophysics in the University Astrofísica in the Universidad Nacional Autónoma de México, and he organizes the summer research internship program for undergraduate students from Mexico and other.
This is very old information.
Okay, that's the one you submitted, so it's not my fault. So yeah, the floor is yours.
Okay, thank you very much. So thank you very much for inviting me. So for the same reason that this information is this title is very long, I didn't choose this title, but this first realistic models of dust in protoplanetary disks, perspective for future observation, blah, 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 blah. I like to choose shorter and more impact titles, and actually I would have chosen wait. No, man. No. I would have chosen the death of spherical dust, no? And this is actually a spoiler of what I'm going to talk. No? I'm going to talk about dust evolution because what the objective of this is to understand how planets form. And planets, we know that the formation of planetary systems is something that happens at the same time that the star is forming. So this is a schematic view of how a protostar is forming actually. So several stages of the planet of the star formation. We have a central object which is growing, accreting mass from a surrounding circumstellar disk, which is sometimes called accretion disk because it contains a lot of gas which is accreted into the star and is what makes possible the star to reach its final mass. But it is also called a protoplanetary disk because it contains also dust, some dust, 10% of dust probably, and this dust is going to evolve in during the whole formation of the star. At the same time, it's going to evolve to form planets. We will form planets from the growth actually of dust. The dust evolves at the beginning, very early in the formation of the disk. It settles in large dust grains settle into the middle plane. Small dust grains remains at different heights in the disk, and evolution is going to take place here. Dust is going to grow from planets, from planetesimals at the first time, and it's going to migrate to the. It's also going to move in the disk and probably migrate to the innermost part of the disk. We are trying to understand how planets form, and in particular, I'm interested in the early stages, in the earliest stages of the planet formation, how the dust grows in protoplanetary disks. And we start from these, which are very small particles of less than 1 micron in the interstellar medium, probably fractals. We have several evidences that they have this shape, this fractal shape, and this is gonna form the disk, and this is gonna evolve to form something we call pebbles, which are rocks, small rocks of 1 millimeter, 1 centimeter. This is gonna happen, we think, due to dust coagulation. So basically, these small particles glue together to form these large particles. Once we have this, we can start other mechanisms to form planetesimals, which are large rock of kilometer sizes of 100 kilometers, and this is gonna evolve to form the rocky core of giant gaseous and terrestrial planets. No, I'm gonna talk about this. We don't know. I'm focused on how this is happening. No, at which age, in which way is this happening? That's coagulation. When do we have pebbles, and when do we start these other mechanisms, and how are they located in the disk in order to be the regions where planets are gonna form? And we can see this because we observe at wavelengths which are very close to this size of the dust, no, of the dust grains. So this is again an schematic view of the disk. So if we observe at different wavelengths, we can see different parts of the disk. If we observe at infrared and far infrared and near infrared, we can see light from the star, which is scattered from the surface. And the surface is tracing the small particles which are located in the atmosphere of the disk. In the mid-infrared, we can see the inner parts of the disk, very hot. And at 2mm and millimeter wavelength, we can see the mid-plane, where the large particles are located. No? This is a typical spectral energy distribution of a disk, and you can see here that the dust emission, this is thermal dust emission, and you can see here that the peak is around 2 millimeter, and you have, this is the optically thick part, and this is the optically thin part. And we are interested in observing both, but especially optically thin. And this is located in the millimeter and centimeter wavelength. And we need to observe optically thin in order to obtain parameters of the dust emission. No? So how can we do this to observe the mid-plane in the millimeter? Well, the millimeter has some advantages we can observe with high angular resolution, because we can observe using the large radio interferometers. And we have two very good, at the moment, we have two very good interferometers, which is the BLA. We have been using the BLA since the 80s. Indeed, the first detection of dust in protoplanetary disks were made with the BLA. The first resolved images were made with the BLA. Now we have IRMA, which is much more powerful in the millimeter. IRMA observed at this range from between the sub-millimeter, but arrive to can observe up to 7 millimeter, and the BLA can observe from 6 millimeter to the centimeter. Okay, so with these two interferometers, we can obtain very good images of protoplanetary disks, and we can observe the dust mainly, which is what emits a millimeter, and we can study the particle distribution, which is easier to say than to do. This is one of the first images of ALMA using the highest angular resolution possible, and it looks very nice. This is the first time we were able, with ALMA, this is it has made possible to obtain these images, which are the image quality of these images are very close to the images we obtained at the optical. And this was a surprise. This morphology was a total surprise. We were expecting a smooth variation of the brightness, but actually we have this, which is bright rings and dark rings. And now we know that bright rings are associated with dense dust, and dark rings are gaps, are regions of low density of dust. So the dust is evolving. What we are looking is the dust evolving. The dust is segregating in several parts. And these are dense parts, the bright rings are dense parts, where probably planetesimals are forming. That was the first disk we observed with ALMA, with the highest angular resolution, because it's the brightest. But we have been observing a lot since then. That image was from 2014. And we have observed a lot of this. This is the DSHARE project. That was the first project that observe a lot of this a blind survey of the disk, and we observe these very different morphology. For example, these are rings and gaps, but these are spiral arms. And we are observing this kind of morphology in a lot of these, and we are detecting very large 100 AUs distribution of dust. But not only this, now at this moment we have observed around 1,000 disks with ALMA. We have resolved an emission, and this is an example. This is a survey of this in Taurus, one of the most famous, one of the nearest star-forming regions. And you can see again a lot of large disks with substructures, but actually most of the disks are very compact and they don't show substructures. Indeed, now we have a statistic that 70% of the disks we have observed with ALMA are actually compact, and we don't know if they have substructures because we cannot observe them, or they don't have substructures. There are several explanations for this. Very recently, we have in this sample of this in Taurus, we have characterized their emission, and this is very important. With ALMA, we were expecting to detect optically thin emission at 1 millimeter. Because this 1 millimeter is the easiest wavelength to observe with ALMA. So we were expecting to observe 1 millimeter optically thin emission, very bright from the disk. Dust emission decrease with the wavelength. So at 1 millimeter, we were expecting to observe optically thin, but the fact that the dust is actually segregated to some regions makes the density very high, and makes actually the emission at 1 millimeter very dense. And this is a study we made several disks. This is the spectral index at different wavelength. Here is from 0.8 millimeters to 2 centimeters. And you can see that there is at short wavelengths, we have this spectral index, which are consistent with optically thick emission. And when you pass the 3 millimeter barrier of wavelength, you have increase in the spectral index, which is associated with the optically thinner emission. So you need to go to wavelength longer than 3 millimeter in order to study the properties of the dust. And this is bad because at 3 millimeter, the emission is very weak. This is the same, but in showing the radius of the disk. So compact disks are here, and large disks are here. And these two lines represent the spectral index of the emission at different wavelengths. When they are very close, this means that it's optically thinner. When they are separated, it means that they are very highly optically thick. So small disks, they are not only compact, they are more dense, intrinsically denser than large disks. And this means that it's going to be very difficult to observe this and to resolve the substructure in these disks. For this, we need new interferometers with much higher sensitivity and longer wavelength, like the SKA or the NGVLA. So the thing is that rings are optically thick now. So it's very difficult to characterize their properties. And the internal part of the disk is even more optically thicker. We can do this with, we can obtain optically thin emission observing with the BLA, and this is what we did we have been doing in these years actually, but we are limited to observe only the brightest part, the central parts of the disk with the BLA, with the current sensitivity. This is super important in an image of the 7 millimeter. This is assumed, and when we observe at longer wavelength, we can even detect substructures. In the substructure, we can detect, for example, clamps we think are related to the formation of new planets. So what do we do? What it has been clear right now is that we need to observe at a lot of wavelengths in order to characterize the emission. We are not sure we can observe here, where the emission is well optically thin and but is very weak. But we can observe a different wavelength. If we can reconstruct the spectral index, spectral energy distribution, we can obtain a lot of information about the properties of the dust. For example, this frequency at which there is the change of the ranging from optically thick and optically thin is related with density. This flux is related with the temperature and the albedo of the particles, which is an intrinsic property of the particles. And this slope, and especially if this slope change, is related to the particle size and other things, chemical composition, internal structure of the particles. This is what we do. We obtain images, high quality images of this at several wavelengths. It's better if we can resolve the substratus, so we can distinguish we can see how the properties change with the substructures. This is from 0.9. This is a shear tau again. This is from 0.9 to 8 millimeter, and we can convert this with several methods into RyA profiles of the different properties. No, this is dust temperature. This is dust density, which is where you see that we have rings are high density and gaps are low density. And this is the maximum particle size. At each radio, we have a lot of particles, not a single particle. We have a distribution of sizes. And this is what we usually measure, which is the maximum particle size we have at each radio. And you can see also that we have oscillations probably related to the rings. And this could be interpreted that the rings are growing particles because you have a lot of density. No? The important thing here for this tool is this number. These are millimeter-sized particles. This is a protostar of 1 megayear, of 1 million years. So, and this is one of the youngest we have observed at millimeter wavelengths. So this means that at 1 million years, we already have pebbles, which is what we need to start to form planets. And we obtain a similar results. In all of this, we have been able to do this characterization of the dust properties. Okay, so 1 million year, we have already ready to form planets. If we have more wavelengths, and this is a very recent work we published, if we have more wavelengths, we can even obtain more information. Now here is the same, these, and these are the same images I have shown there. But here is a very short wavelength, which is related to the temperature. And this is an intermediate wavelength between the most longer wavelengths. And if you have more wavelengths, you can even model more parameters. No? For example, this is again temperature, this is density, this is the maximum particle size. Similar results, this is colder, and this is thanks to the very short wavelength. And this is very important. If you have very short wavelengths, you can also constrain very well the temperature. And this has an effect in all the other parameters. No? The maximum particle size is the same, but these two are very important for this tool, is porosity and composition. We are starting to see differences in porosity and chemical composition in the spectrum. Okay, so this is what we can obtain from the spectrum, but ALMA has a lot also to observe polarization. Polarization is a fraction of the total intensity we receive. But it gives a lot of information, a lot of complementary information we can combine with the spectral energy distribution. And this has been made in interstellar medium with a lot of instruments, but it has been possible to explore at these scales with ALMA. This is the best example, again, HL tau, which is the best observed disk we have with ALMA. And this is observations of polarization at mid-resolution. Here we are not resolving the substructures, but we are looking at the global emission, and we can see the polarization. And this is 3 millimeter, 1 millimeter, and 900 microns. And what you can see here is a difference in both the polarization degree and also the polarization pattern. Here, at short wavelength, we have a pattern which is parallel to the minor axis of the disk. The disk is inclined, so you have this orientation. But here, at a longer wavelength, what you see is a circular pattern, a very different pattern. And here you have a combination of both. No, so this change with wavelength of the polarization implies that there is a polarized spectrum. No, and we can obtain information about that. How we interpret this? So, which are the light of source of polarization, of scattering? So if you have a protostar and this is the disk is very bright in infrared. And the disk illuminates the disk, and it can interact with the surface of the disk with the small particles, micron-sized particles in the atmosphere and scatter the light. And this is polarized. And this can create a circular pattern. But this is not the explanation for the circular pattern, because this is happening in the infrared. In the millimeter, the star does not emit. What emits in the millimeter is the mid-plane, where the large particles, millimeter and centimeter particles, are located. But they can they emit light at millimeter wavelength, and they can encounter another particle, that's particle, and this can arrive the observer, and this emission is also polarized. This is called dust self-scattering. Dust self-scattering, and you have a dust grain in the disk, and there is light thermal dust emission from other grains, which is more or less the same size, and this will interact with this dust grain, and if you are the observer, you will see a polarization in this direction. But you have dust grains everywhere. So actually, the polarization you should see is zero, because all the vectors of the polarized vectors should cancel out. But if for some reason you have more emission in one direction than in the other, you will see an excess of polarization in one direction. And this is going to be very weak, because it's only the excess of emission you are receiving for all directions. But you can detect this, and we detect this in the disk. In the global emission of the global polarized emission, if you have an edge on this, what you will see is that the vectors, because a dust grain is receiving a lot of emission from here, but very low from here. So you will see that the polarized vectors are in this direction. If you have an inclined disk, you expect something which is parallel to the minor axis. So this is the explanation of this observation. There are other mechanisms which is different from scattering to produce polarized emission from dust grains, and it is that dust grains probably are elongated. They are not spherical, and if they are elongated, they intrinsically emit dust polarized emission. This is just the thermal emission, but polarized. And you can have several scenarios here. So you can have no any align. So this will generate no polarization, because you will assume very different orientations. And if you have some alignment for some reason, you will have some polarization in one direction. No? So this gives you the way to interpret this. So this is how we think, what we are looking. Here is optically thick. Optically thick is a lot of density. So the probability of scattering is very high. So we are looking at dust self-scattering, and we are recovering this pattern, polarization pattern, which is parallel to the minor axis. Here, what we are looking is optically thin emission. So we are looking directly to the thermal emission from elongated particles, and they should be aligned in order to produce this. And we don't know what is aligning these particles, but this is the only way we have to explain this. Something important here is polarization can use to trace density. And indeed, we have done this with high resolution. This is, again, a shell tau. You remember that we have here high density and low density regions. If you observe with polarization, here is a zoom, you can see differences in the polarization pattern between gaps, which are circular, and rings, which are parallel to the minor axis. So this means that rings are optically thick, and gaps are optically thin. This is what we were expecting. But we have modeled this polarization, and you can see here the variations of the optical depth, which is related with the density in the disk. No? From this modeling, we see that we have 10 times optically thicker emission in the rings than in the gaps, and this means that approximately 90% of the dust mass is stored in these rings, which are optically thick. No? And this is important because we need most of the dust is stored in regions where we cannot observe actually very deep, because it's optically thick. No? Polarization is also highly sensitive to particle size. This is albedo. This is the size parameter of the dust. So this is the A is the radius of the maximum particle we have in the distribution, and this is the wavelength. So here we have large particles compared with the wavelength. And here we have small particles compared with the wavelength we are observing. No? And this is the albedo. This is the probability of scattering. So small particles have very low probability of scatter light, and large particles have very high probability of scattering light. But there is also the polarization degree due to the scattering. No? So this goes in the other way. Small particles, if they are able to scatter the light, they will produce highly polarized emission. Large particles, on the contrary, if they are very likely to scatter the light, but they will not produce a lot of polarization. So there is a small region here around this number when the wavelength we are observing is 2 times p, the radius of the maximum particle size, where we can have probably a bright polarization. So we can use this to characterize particles, the size particles in the disk. And this is another way to see this. This is the maximum grain size, and this is the wavelength, the curve. We will have a different wavelength for polarization. So imagine we have 1 millimeter dust grains in the disk. We expect a lot of polarization at 7 millimeter, but very low polarization at all the other wavelengths. Imagine we have 100 micron dust grains in the disk. We expect a lot of polarization at wavelengths around 1 millimeter, no polarization or very weak polarization at 3 millimeter, and no polarization at 7 millimeter. Okay, so remember that this is for spherical grains. So this is the way to explain. So this is something we can use to characterize the dust particles in HL tau. At 1 millimeter, we have self-scattering because we have this pattern. At 3 millimeter, we have not that self-scattering. This is a very different mechanism. So we are in this region where we have emission, we have polarization, dust scattering at 1 millimeter. So this means that HL tau has particles of 100 microns. And this is the problem here. And this is the problem we have been discussing for 10 years now. So the analysis of the dust continuum spectrum implies that we have millimeter-sized particles at 1 million years. But the analysis of the dust polarized spectrum indicate that we have very low, much smaller particles in the disk. These are pebbles. These are going to form planets. This is very far from starting to form planets. So this is a problem because both formalities are correct. So any assumption should be incorrect. And the assumption is, the assumption we now is very clear is incorrect is this. We are using optical properties of spherical dust. And actually what all the grain growth models and what we are expecting, and we know that, but this is easier, is that particles are fractals or are porous particles, no? And this has very different optical properties. And this, we are sure, can explain the difference between both results. So in the solar system, this is a problem very similar to what have been found here in the Institute of Astrophysics. This is, for example, the Rosetta comet. In the solar system, we have the comets, and the tail of the comets are composed of dust, which is more or less the dust which was in the protosolar disk. So if we can observe the tail of the comet when it is approaching the sun, and we can with the Rosetta satellite, we can observe different directions scattering the light of the sun, and with this we can construct this, and we did indeed, and Olga in a paper studied this phase function, which is the amount of light which is scattered at different scattering angles, and the degree of linear polarization at different scattering angles. Green is the measurements of Rosetta, and black is an ellipsoidal dirty ball, which is this dirty cotton. That was the only particle the only material able to reproduce this result. So this means that particles in the tail of this comet are highly porous and highly absorbent. This is something similar we are doing in some protoplanetary disks. I mentioned earlier that the star emits in infrared, and you can detect scattered light in the atmosphere. In the atmosphere of the disk, we have very small particles, but this allows to study different scattering angles. If we have this, if we are observing this, and we have this for several disks. And what we have found is that the phase function, this is the this is the polarized flux at different scattering angles, which are different points here in the azimuthal angle, in the azimuthal angle in the disk. So we found two categories. This category 1 is only reproducible with high porosity with fractal particles. And this category 2 is only reproducible with low porosity, like something like this. So this is what we have probably in the disk. Actually, not spherical dust, and this has very different optical properties. Optical properties which are extremely difficult to calculate or to measure in laboratory. We have indeed some approximations. We can use the hollow sphere to calculate this. What we usually have in all the models of radiative transfer is spheres, compact spheres, solid spheres. But we can simulate, we can calculate, we can estimate porosity using this approximation, the hollow sphere, which is essentially a sphere with a hole, a spherical hole at the center. We can use Mie theory, which is analytical, to calculate this. And this is not bad for the spectrum, to explain the spectrum, because it reproduces very well absorption, but it's very bad for the polarization properties. There is another one, which is effective medium approximation, which is porosity is treated like vacuum, no? So if you have something which is highly porosity, you treat porosity like another chemical component, and you have the refractive index of the vacuum, and you obtain an average refractive index, and these reproduce more or well qualitatively the properties of polarization, but it's still an approximation. We did this, we used the effective medium approximation to estimate, to make some predictions about what happens when we consider porous particles instead of spheres. And remember, this is the effective polarization of a sphere, and at different wavelength we can detect polarization from a single size, a very narrow range of particle sizes. When we consider polarization, what happens is that this range increases. So for highly porous particles, we have a single particle with a single size, a size distribution with a single maximum particle size can produce polarization at a lot of wavelength, and this happens for different polarization. So what we are expecting now is that we can detect polarization that's self-scattering at a lot of wavelengths. In the case of facial tau, we predicted, we made an estimation, raw estimation of the porosities should be higher than 70%. This is we made subsequent observations of facial tau. This is now a lot of wavelengths: 7 millimeter, 3 millimeter, 2 millimeter, 1.5, 1.3, and 800 micromillimeter. And you can see that here we can see a more sample change of the polarization pattern. And then we can separate both emission, the thermal emission. Here we are assuming that we are looking at the thermal emission, polarized thermal emission of aligned particles. And here we are dominated by the self-scattering. This corresponds to this, and this corresponds to this. So here dominate thermal emission, but the self-scattering is actually flat. It is not what we were assuming before, that here there is not self-scattering, and here is a lot of self-scattering. It's flat. So this is consistent with moderately porous, elongated aligned particles using this approximation of effective medium. There are strong implications of this. If particles are porous, this means that the size of the particles are actually larger than we are measuring. So we are in a more evolved stage to form planets. And also the dust mass is larger. We are actually, when we are able to measure the mass, because we are observing optically thin emission, we are calculating lower mass than actually is if we are considering porous dust particles. So it is clear that we need to produce models for the emission and polarization of more realistic dust particles. But as I say, this is very hard. But this is what we thought it was a very good PhD project for Gonzalo, no? And thanks to the Severo Ochoa program which has helped to travels of me and Danny and the PhD fellow of Gonzalo, we are advancing on this. No, Gonzalo is working here and is co-advised by Danny and me, and he is doing that. He's calculating porous particles. So we spend some time constructing these porous particles. These are spheres with random holes, and we can produce any porosity we want. So here is from 0.3 to 0.9. Higher porosity, we need to produce fractals, and these are some examples of fractals. This is 0.94 porosity and 0.99 porosity. These are animated GIF to see how is the internal structure. And we use the T matrix to calculate the T matrix code to calculate this. T matrix to calculate this, and ADA to calculate this. And this is very hard. This means a lot of computational time. We observe, at the moment, we have been able to calculate all the particles at 4 wavelengths and all the porosities and different particle size from 0.01 millimeter to, micron to 1 millimeter. Okay, this was thanks to MISLI. MISLI is a supercomputer we have in UNAM in Mexico City, and we obtained. We asked for 250,000 hours of computation. We got at the end 700,000 hours of computation, all of the time using 64 cores, but some periods of the 256 cores. And we have already submitted a paper which is very close to be accepted. And these are some of the most important results we have found at this moment. This is the absorption. This is the absorption coefficient. This is the easiest part. This is the absorption coefficient versus the frequency of the light. This is the extinction, which includes also scattering. With the frequency. So what you can see is the black line here is always here at the top, and this is the sphere. And as you consider more porosity, you have less absorption and less extinction. This means that you have, when you use spheres to interpret a porous disk, you are actually calculating less mass than is the disk with porous disks are more massive than what you obtain when you are considering spheres. This is the same for the effective polarization. No, this is the albedo. This is the albedo. The albedo multiplied by the polarization you have. This is the effective polarization. And this is, remember that, well, first here you can see that you have a maximum of the polarization. This is the maximum particle size. So, and this is the different wavelengths. So as you move in wavelength, you see the polarization, mainly the polarization of different particles, no? Longer wavelength, see the polarization of larger particles. But if you look at one wavelength, 1 millimeter, which is what we usually use to trace polarization, in black you have the sphere, and this is what I have been mentioning a lot of time here. You see polarization of mainly one particle. But when you consider porous particles, you see polarized emission from a very different range, a very wide range of particles. So you can see actually the emission of particles of a lot of particle sizes. And studying this this behavior, you can even, in the future, you can even constrain porosity. The difference here with the real calculations, with the effective medium approximation, is that the polarization actually increase. When you have porous particles, you increase the polarization, you don't lower the polarization. Actually, we have much more information because we are calculating the scattering matrices. So this is something we can put into the radiative transfer models, into the radiative transfer codes, and obtain predictions of how we will observe this, because this is much more complicated than only seeing the other plots. No, but here you have the F11 term of the matrix. This is the amount of light which is scattered at different angles, scattering angles, and this is the polarization degree at different, you obtain at different scattering angles. So look at this, for example, this is a different wavelength. Look at this is a small wavelength particle of 1 millimeter. This is a large particle compared with the wavelength. This is what you expect. The black line is what you expect for a sphere, no polarization. And this is what you actually get when you have a large porous particles. You have a lot of polarization. But not only this, there is a lot of structure in a different. There is a lot of structure in the polarization with different scattering angles. And this is important when you use this to explain emission in radiative transfer code, because you have emission from several scattering angles. The spectrum is very different now. This is for particles with 100 microns. So you expect polarization here at short wavelengths and no polarization at large wavelength for all kinds of particles. But for large particles, you expect a lot of polarization when you have polarization at all wavelengths when you have porous particles, and you don't expect emission at short wavelength when you have only spheres, no? So this means that if we are able to observe at this large wavelength, we will be able to observe larger particles and characterize the properties of larger particles, no? But the problem is that sensitivity now with ALMA is very good here to observe polarization. Here at 3 millimeter is not so good, and the dust is very weak. And here 7 millimeter and longer wavelengths, we don't have sensitivity to detect dust polarization. We don't even have sensitivity to detect dust emission, no? So this means that this is important for the new generation of radio interferometers, the NGBLA and the SKA, which will be able to observe with much higher sensitivity at longer wavelength, and maybe we can observe polarization and study the properties of very large particles. So I'm finishing here. This is the ongoing work. We have still to Gonzalo has to complete the current calculation and extend to 1 centimeter. For this, we are planning to continue using MISLI. We have been using MISLI for 1 year. We are applying for more computation time with MISLI. But this is very difficult for the largest particles, so we are considering to ask for a tiny Mare Nostrum, or using GPUs, we are exploring this, or even buying computation time for private services. Interpolation to any porosity and other chemical composition, we have been able to calculate only one chemical composition, and we are not even sure that this is the correct one. So we need to calculate other chemical composition. We are exploring the possibility to use neural networks. This is not so difficult. And laboratory tests here in the Condulab in Granada. Realistic radiative transfer models. We need to plug this into radiative transfer codes. We have also made some advances on this, thanks to Severo Ochoa, which had Miguel Jáquez, who was here last year, working with Danny, Olga, and Gonzalo, in order to start to produce radiative transfer codes of this with particles which are not spheres. This is a case for irregular particles. This is not what we want. This demonstrated that solid irregular is the same as spheres, but that was the first step in order to construct these models. To now Gonzalo can use his matrices of porous particles. And finally, observational prediction from the new generation radio interferometers, the SKA and the NGBLA. Miguel also is working on that, but this is gonna need a lot of computation and new imaging methods for radio interferometry. And this is actually the things that we are working in Mexico, while here are working on the dust grains calculations. And I will stop here and we'll take questions. Thank you very much. Do you have any question? Fine.
What do we need from observations to infer the porosity? Now we are assuming the porosity, but if we observe a number of wavelengths and fit that polarization, do we know exactly what is the porosity in the dust?
I think that the answer is to observe up very different wavelengths. These are the preliminary results of Gonzalo. We are limited to 1 millimeter, but here you can see different behaviors of the polarized spectrum at different wavelengths, with different porosities. So if we are able to measure polarization at different wavelengths, we are able to constrain porosity, obviously with an error. Ideally, what I would like to do is to do the same that is made here at infrared, at radio, but this is very difficult. But we have been talking that this is not difficult if we have dust surface scattering in the whole disk, and we are observing in the rings, for example, and we can construct different. We can observe different scattering angles, and we can construct the phase function in the millimeter, which is will give information about the dust grains in the midplane. But for this, we need a lot of high angular resolution. This is, I think, still very far. I will be retired or dead at that point. But with higher angular resolution, a millimeter wavelength or 1 millimeter, we can construct potentially the phase function and see the porosity. But I think that the best hope right now and for the future is this: observe polarization at different wavelengths and construct this. This is very easy if you have the sensitivity here.
Is that available now, or do we need?
No. We can observe only here now polarization, and sometimes here at 3 millimeter. Forgot about this. This is impossible. This was very hard to do in HL tau, which is the brightest at 7 millimeter, which is this one. We got 4 pixels with polarization, and this is the brightest one. We need a 10 times more sensitivity at least at this wavelength, and this is only gonna happen with the NGBLA at this wavelength. With SKA, we hope to observe here, and this is gonna be relevant for very large particles, no? For 10 centimeter, one and between 1 and 10 centimeter.
Question on Zoom.
Okay.
So, Ionis, can unmute. Can you maybe repeat that closer?
It's mute.
Yes.
Yes, okay.
All right.
They're unmuting.
Can you hear me? Yes, thank you. Thank you, Charlie, very much for the nice talk. That was very interesting. From the theory side, I have a question.
I think it's better if you guys.
Okay.
Yeah. Do you think there is a possibility in these objects to produce also circular polarization, maybe through the nice porous dust grains that you have created, or through different layers of the material?
Mayra has also a question. Oh, sorry. What is writing the question, Mayra?
About identity transfer model considered non-spherical grains. Lucas mentioned that one of the main difference between spherical and non-spherical dust is the mass equilibrium time twist. We have more massive disks in the case of Porous, almost spherical grains than it is spherical grains. But I'd like to know what happened temperature. It is the effect of the spherical grains in the temperature. As you know, the dose opacity control everything, particularly not only the emission, but also the temperature. Temperatures are going to see how can change the.
This is a very good question. This is a very good question. I don't know because we have not worried about that, but I know the absorption is less absorption of porous, so I think that you will get colder disks, right? Colder disks if they are porous.
The temperature the term between lines is the difference between lines and form. And I guess to calculate the emission, we can also calculate the temperature, assuming in a consistent way it's not very high those trends. I encourage to do that.
There is another important consequence of porosity is that stability of the shocks. And some simulation has shown that when you have fractals, they are more stable when they collide, and they can grow to larger sizes. But yeah, this is important. We need to constrain the porosity and then see the effects in all the other parameters. So this is the question. Do you think there is a possibility to create circular polarization in these systems? Maybe due to an inherent asymmetry of your porous dust grains or superposition of emission from different layers? I think the answer is yes. Danny is moving his head. I think I have answered this, asked this to Danny a lot of times. He always says yes, of course.
It's instrumental, or let's say it's an effect of the observation. I mean, if you have irregular particles, you have particles and mirror particles, and if mirror symmetry is not broken, then you cannot have an essential circular polarization. But if you look at the center of the disk, even if you have mirror symmetry, you will get some circular polarization when moving to the right, and some circular polarization with the opposite sense when moving to the left. And when integrating the whole disk, you will get zero. But that's an observation effect. That's not something essential in the dust. And it doesn't matter if particles individually are not symmetrical, because you will always have a mirror particle for each particle. You will always have a right hand for your left hand.
This can be investigated with the radiative transfer codes. When we have, we construct this and we pass the polarized emission through more material, no? But we need to look for scenarios which are possible in the disk. But the thing is that circular polarization is going to be always very, very weak. So this is a completely different. This is something which is very far from the detector.
It's impossible to measure with SKA and GDL8.
No, we need to do the radiative transfer codes and see, because in the radiative transfer code you can have also the circular polarization. Probably will be very low. I don't know. Actually. Another question? Ruan?
Thank you, Charlie, for this talk. I was wondering, I mean, you mentioned that spherical particles are okay for spectrum, but not good at all for the polarization. are the porous good for polarization, but are they good for the spectrum as well? Because maybe you mentioned it, but I missed it, that.
No, I mentioned this.
Anything
Correct.
about porous particles that can reproduce spectrum? Can they?
I don't know how to. No, what I mentioned is that the approximation of hollow spheres to reproduce spherical, as Danny says, always bad. No, what I say is that hollow spheres, this is good to estimate the characteristic of the spectrum of porous particles.
Oh, okay.
Okay? Because it gives you a okay absorption coefficient and extinction coefficient, but it cannot explain the porosity. The polarization properties are very different from the reality. This can explain more or less the characteristic, for example, this, that with porosity, we make wider the probability of detecting polarization, but it implies lower the polarization, the effective medium approximation. And this is not what we are seeing when we have the real calculations. What we actually see is that polarization increase the polarization. The porosity increase the polarization.
If I may relate follow-up question with that, you said that you have your scattering matrix that you can plug in your RT model. Have you done it?
No. This is the next step.
Okay.
We have made this, which is with irregular particles, because we got access to a large database of irregular particles, hexaederals.
That is for compact irregular particles.
Right.
The answer is yes for compact irregular particles, and they are working on the porous particles.
Can I take the scattering matrix and put it in my code?
Yeah.
Okay.
But there's something else.
I don't have any code.
When I deal with my question, we can do that regarding the scattering properties, but we cannot so far produce the thermal radiation of invisible particles. So we are considering spheres for the thermal radiation and porous irregular particles for the scattering.
Okay.
That's the point. At this point, that's what we are.
But this should not be very difficult to measure, right? Another student. More questions? Mayra, three comments, okay.
About the polarization, along with the square kilometer array and the new delay generation, because some protoplanetary disks, as you know, show some evidence of prejudice.
Yeah.
And this can prevent the polarization. I don't know how you handle this issue.
Yeah, but this is for this, I think the answer is to study the polarization, because free emission is not polarized. So if we can observe polarization, I mean, what is mentioned in Mayra, which is very important, and is the hardest, the most important aspect of observing with SKA and NGVLA. When you go to longer wavelength, you have a different mechanism, which is a free emission from photoionized gas or the jets, no? But this emission is not polarized. So if we can observe polarized emission with SKA and NGVLA, we can actually solve this problem that we don't know what we are detecting with SKA and NGVLA. No? And this is a way, this is something a lot of people is trying to understand. Okay, we have these interferometers that allows to detect dust, but actually the free emission is brighter at this wavelength. So polarization could be an option, and for this reason, we think it's important to do these predictions from the new interferometer. Another, you have to.
I agree, considering sophisticated models and taking into account non-spherical, that's very useful. But as you know, we are several uncertainties in those
Chemical.
properties, for instance, composition, the size, distribution of the grains, perhaps combining several observational diagnostics. For instance, the James Webb is obtaining very amazing spectral energy distribution with features of the ice, so that we can translate composition. So,
Oh, sorry?
James Webb has obtained.
Ah, this way, yeah.
James Webb has obtained spectral energy distribution with very clear features for ice, where we can constrain the composition of the membrane. So combining these two facilities, the radio spectrometers plus the infrared telescopes, like this way we can obtain a very realistic
Yeah, absolutely.
for those great measures.
I think it's necessary to combine a lot of information. No? In the millimeter alone, what we are trying is to put more wavelengths and try to find. I mean, all these parameters have some effect on the spectral energy distribution. So if you have very good spectral spectra, in principle, you can fit this, but as you see here, it's very difficult. We have a lot of uncertainty. No? For sure, you need to combine with other wavelengths in order to discern which is the chemical composition. And this is very important. We don't know the chemical composition. Every word uses a very different chemical composition. This is why we need to make all these calculations. Gonzalo needs to make all these calculations at very different chemical compositions, because we need to be able to reproduce any chemical composition, porosity, all the properties. No? But in 1 year, we were able to only calculate up to 1 millimeter, at millimeter observable, at 4 wavelengths, and 1 chemical composition. What's another?
My final question.
Okay.
I agree to consider non-spherical grains, the relative Protoplanetary model, but I am a little bit worried because we have spent a lot of computational time to.
The relative transfer cost.
Yes. This is my question. How long would they?
Once you have the
model with realistic opacities, you say that you are putting a super computer in Mexico.
But Gonzalo is producing a database, no problem.
Yeah.
That you can use in your code.
So it's the same.
And you don't have to compute it. Yeah.
You don't have to compute it. If you have to calculate at the moment, it's impossible. No, we are producing all the scattering matrices, so you have all the information. So you want your code only need to know which is the wavelength and which is the dust grain. And what they do right now is to use me to calculate the optical properties. But the idea here is to use the matrices. More questions?
All right, there's no more questions. Thank you, speaker.
Thank you.
Condular, por favor, permitir condular. Thanks. Cosmic blast.
Condular? No.
Condular,
¿No suena mejor cóndula? Siempre tengo problemas contigo. Por año te estuve citando con otro completamente diferente. Por años.